Hello everyone. I am really excited for this video. This is second to last one in our series on While True Learn, where we play a bit of the game so we can get a sense of how certain machine learning algorithms are used in the real world and some practice applications, and then we build one for real. And as always, I'm focused mostly on making sure that you guys can use these things immediately and hoping that you'll research the math and research how things are working later. But let's get right into it. So here's some footage. We've got about 18 minutes to get through from the game, and we're starting in right where we left off on the last one with MLPs. And you'll remember from the last time that we looked at perceptrons, we were looking at a Rosenblatt perceptron, and it was really simple. I had you code the whole thing. We used PyTorch. This time we're going to take an even more simpler route and look at it with sklearn. And here's the difference between them. So unlike Rosenblatt's perceptron, present-day perceptrons can predict more complex or nonlinear dependencies depending on their activation functions. And the most common functions inside these activation functions are tanh, ReLU, and sigmoid. Last time we used sigmoid, this time we're going to be doing ReLU. And gradient descent is one of the main differences, where gradient descent allows us to back propagate through our neural network that we've created. And that's why in this game you have to put it before the actual perceptron so that it can help it train. That gradient descent helps the perceptron converge quicker. It speeds up the time that it takes to actually get to that minimum amount of error, both in real life and in the game. And it does that by essentially visualizing the entire error landscape as if it were a graph with like mountains and valleys in it, and by descending based on a given gradient, based on the slope that it's currently feeling. It's really, really cool. But perceptrons, you're going to find them in every single example of a neural network, whether that is a brand new one like DALL-E or an older one like GPT. And once you finish these videos, I strongly recommend you go and hit my hands-on NLP playlist as well to get into more modern approaches to these things. You're going to find, though, that having a basic understanding and having a really solid basis in how to use machine learning algorithms, especially decision trees, which we've already gone over, especially logistic regression, which we will go over later, especially these perceptrons and very like one-layer neural networks, it will help you use the more modern stuff like transformers a lot more effectively and understand those problems a lot better. So let's read this. Deep neural nets. There are neural networks that solve the so-called XOR problem, the exclusive OR problem, an unsolvable problem for Rosenblatt's perceptron. They have one hidden layer between the input and output layers, and such networks are called non-deep or shallow. If the network has more than one hidden layer, it is called deep. That's not so true anymore. Normally it's about 6 or 7, but the deeper the network, the more complex a relationship it can actually describe between your data and your outcomes. I encourage you to experiment with this because you're going to find really quickly, if you use that MLP the multi-layer perceptron that we looked at last time, just adding more layers does not help you actually. You can't just add more layers for more accuracy. You have to actually change the data that you're putting in as well as adding more layers. It's a garbage in, garbage out is something that a lot of machine learning engineers use to describe this. Do any of you see what I'm doing wrong here? That has to be as accurate as possible. And this is something that you'll see in the real world too. This is where we... because of that 9% inaccuracy rate, I'm trying to keep that accuracy really, really high by adding a decision tree afterwards. Or not a decision tree, but a... what was that? Was that a perceptron that I used before? No, I think that's the pre-trained genetic. But sometimes, so the perceptron is really fast, but it has a higher error rate than normal. And so in order to keep that up above 97% accuracy, I added an RGB sort afterwards, where even though it was slower because we were basing it on accuracy and time, it actually worked. And one of my favorite parts of this game is actually buying this stuff in the store because it's real. Like, you will find real machine learning scientists end up using bigger hardware. Like this is, I'll show you my hardware right here, and the filters being weird with it, but it's an i7. Let's go over the ReLU first before we get into that. So ReLU is a really fun activation where everything that's negative just gets leveled out to 0, and everything that's positive stays whatever it was. It's X. It's an identity function, essentially. This helped the perceptron learn to essentially fold space to follow the exclusive, or to solve the exclusive OR problem. Really cool stuff. Recommend you dive into it. The ReLU is not even state-of-the-art anymore. It's not used as much. We do more things like the GELU and other things. We'll get into those in my Transformers videos if you're interested in them. But just like in this game, real machine learning engineers and real machine learning scientists actually do buy those more expensive GPUs and the more expensive CPUs for just to increase their processing power and the size of a data set that they're able to store in memory, and the size of batches that they're able to actually put through these, so that you don't need as many of these load balancers, where you're seeing immediately, this is excellent timing, the load balancer and both of the gradient descents, because they process things too slowly, are completely maxed out and slowing down. They're information bottlenecks, and so hardware can help you to mitigate some of that. I would recommend very seriously going through and figuring out how to deal with memory in machine learning, though, mostly because that memory can save you so much. Like, memory management is way more important than hardware. Learning when to use torch.cuda.empty cache can be huge for the models that you're able to run and the amount of data that you're able to process during training. It's fun looking back at these videos too. These are the first time that I ever played the game. So we're going to buy a really important piece here, stochastic gradient descent. And we'll go over how that's different from regular gradient descent in a second. And that's what I'm going to show you how to use today. We're going to use sklearn to do stochastic gradient descent in both a multi-layer perceptron and in just a classifier. And I'll show you why sklearn is so cool for that kind of a thing. Even though it's kind of basic, it helps for like you could do real work for real companies just using sklearn, which is fantastic and amazing, and they will think that you're an absolute genius, which is cool. It's fun, and it should be an incredible step up for everybody to help understand why you would want to customize any of this stuff. And this is a cool thing too. There are a lot of cases where one of the most important metrics to have in real life, I wish in real life you just got the processing speed at just whenever. That would be absolutely amazing. But you should get used to trying to measure your processing speed as you're doing things, so that you can see immediately that, you know, if I add this decision tree here, how fast is it going to go, and am I creating an information bottleneck in my pipeline? Let's skip ahead. Nice. This is one of those where you get to see that the engineers at Luden.io really put a lot of thought into how they wanted people to solve each of these problems in order to get gold. They engineered it so that the order of the data that comes out in the stream actually, or I should be pointing this way. I'm sorry, it's mirrored. The order that data comes out of the input stream, you see immediately some red triangles right at the beginning that get sifted into that top one to keep it just under 50% accuracy right at the beginning, so that it takes literally 0.1 seconds over what it should take for a gold. And so that's the problem that we end up trying to solve. And honestly, that's something that I've had to deal with customers in the past, where they are trying to hit certain metrics for processing speed, and so you have to rearrange things to make sure that they actually process quick enough. Because if you don't, then you run into the problem of not fulfilling the business requirements of customers, which is like the cardinal sin of software engineering. I got really confused by this. Let's see. Oh, so this is how I ended up solving it. Just that one teensy bit of accuracy extra, and all of a sudden we're under the amount of time that it takes. So stochastic gradient descent, as opposed to regular gradient descent, that stochasticity is initializing randomly and using a bit of randomness within your descent. Sometimes that can cause extra error during training, but it ends up making it so that your model is able to converge faster. And this is what happens if you try to use both. It'll just do it at the same. Oh man. Oh, I hit test run instead of train. So you'll see that number will shoot around. You get up to 100% error, and it bounces around a lot, because stochastic is not the same as random. Stochastic is statistically probable, but described by a random distribution really well. It's close to random, and a lot of people use those interchangeably. But that stochasticity allows you to almost guarantee, in real life as opposed to in the game, that you don't converge in what's called a local minimum instead of your global minimum. Essentially on that landscape, with the highs being far away from your target and the lows being really close to your target, sometimes you'll go down a little bit and then have another peak where your global minimum is all the way over here. And that stochasticity can allow you to bounce out of those local minima, which is really helpful in practice. You'll see that one of the things that I do pretty often to optimize things is just instead of adding a trash can to get a silver, I just let it run and fill up that memory a little bit. I think it's funny. Maybe it's not really. Here's a little question for you guys. I think that you'll be fine to answer it. What why do you think that the perceptron for shape is slower than the perceptron for color? Leave an answer in the comments and have a discussion. And again, this is almost diabolical, the level that the engineers that made this game thought about it. Because you can see, if you look at the data, or I need to point this way so you guys can see it. If you look at the actual data over there, you'll see 5 plus 5 plus 3 plus 2 plus 2, right? That's 10 plus 3 is 13 plus 4 is 17, right? And 17 is the exact number that you need to get, but with 94% accuracy. So you can miss one, but each of these has a 9% error rate. So you can see I'm getting 16, which is one fewer than what we actually have. If I add in the green, then it doesn't work because the accuracy goes too far down. I can keep a good amount of accuracy, but I'll miss one. It'll get sifted into either the squares or the circles where it shouldn't be. Can't keep training. How did I finish this one? Did I just leave? Oh, I just left. I just gave up. Awesome. Ooh, isolation forests. I think I'm going to do another video on random forests and isolation forests versus those decision trees. Hopefully that should be helpful. But you can end up using them almost interchangeably just depending on which problem you're trying to solve. I tend to go straight for a random forest, not even do a decision tree, because a random forest is essentially just a bunch of decision trees, and you just take the one that is most statistically matched to your data set to solve your problem. It's like running a whole bunch of different decision trees just randomly and just figuring out which one's the best, what gets you the highest accuracy. And then you can draw some really interesting insights from what that random forest used as criteria to determine between things. It's really cool. Let's skip forward a bit. Using the isolation forest to take only the blue. Oh yeah, that makes sense here. So we can see that we only want the blue circles in the top one. Everything else can be put in the bottom one. So this was pretty much made for an isolation forest to get gold on it, especially with the amount of time that it takes to process, because it's almost a full second for each thing. Fun. And I lost 149 for that job. Amazing. And we made it to the recurrent neural network. Let's get into processing things just like last time. The last time that we used any sklearn stuff was with the decision trees, and if you've checked out my video on machine learning in one line of code, this should look incredibly familiar. We're going to use that same colors CSV that we've used before. This is just a pseudo data set showing exactly how you end up needing to process these data sets. You can have as many features as you want, but you just have to make sure that those features get processed correctly, and you have labels. One column of labels for supervised learning. We can go over unsupervised and reinforcement learning and other paradigms, but let's do this first. So we want stochastic gradient descent, and we'll just call it stochastic gradient descent. And I'm actually going to do this as a Jupyter notebook instead of just a script. IPYNB. Perfect. Okay, and so we want to import both stochastic gradient descent classifier and a multi-layer perceptron classifier that uses gradient descent. So from sklearn.neural network import MLP classifier, and from sklearn.linear model import stochastic gradient descent classifier. Let's see, what did it actually say about that? Linear classifiers. Yeah, it's just a linear model with stochastic gradient descent learning. Perfect. And then import pandas as PD. And we're just going to run this. And then we want our data frame to be pd.read CSV, and we're going to feed it the colors. Again, this should look exactly the same as last time. So we can see our two features, the grade, and if you don't remember, this is classifying whether or not a student gets into MIT or something. Because that was a problem that we saw in the game. We're going to actually take the exact same mapping that we did before. You can use any sort of encoder. You can use a tokenizer for this. You can use the sklearn label encoder. You just need to map everything to numerical. And so I'm just going to copy and paste this. This is the exact same one as our previous decision tree one. So then if we actually, let's do df.head again so we can see exactly what it looks like. Oh no. I think that should still work because we mapped it correctly. Yeah. Hold on, let's check some things. And df 0. Let's say df pass 0. Oh, crazy. Well, hopefully it works. It worked last time. We just want grade and color, and we want x equals df features, y equals df pass print xy. Is it because they're floats and this is trying to print them? That could be. We're gonna initialize these exactly the same way. MLP equals MLP classifier. Max iterations 1,000. Experiment with that because I'm just trying to raise it. The default is 200, and it's difficult to converge within just 200. But I mean, maybe it would. It probably would with a larger data set, but because ours is so incredibly small, we'll have to make do. And so let's train sgd.fit xy. And we're just going to do exactly the same thing, but with MLP instead. No, these are nans. Huh. Weird. I just ran it again and all of a sudden these are numbers and they're fine. So this should work swimmingly. Yeah, it worked just fine. I don't know why rerunning it helped. Oh no, yeah, I do. I ran this cell too many times because it's trying to map things that don't exist to things that were already in the data set. That was the problem. Sorry about that. But then now that we have two trained models, we can do A and B equal, and we'll do two predict functions. And this is exactly the same as before, and MLP.predict. Oh, I need to print them. All right. So it looks like if we are 0 and 0, which is, looks like they have an A and they are red, then they pass and they get into MIT. And I'm going to just copy and paste exactly the same stuff that we did last time. So if they are red but got C's, and then if they got A's but they are green, and then if they got C's and are green, looks like they don't get in for any of those. So this did converge and it did learn on our data set. I can't say that that data is incredibly accurate or good, but it shows you how to process things with multiple features into an actual model. And then we can do sgd.save model. Where are you? Let's do score. And we'll do scores equal to do. We'll just initialize it as a list and then say scores dot append. And then scores dot append MLP dot score x y. Yeah, they're getting 100% accuracy. They worked. Great. And so these are then models that you can save. And I'm gonna look that up real quick so that I can, because I would love to show you guys how to save and load these models. Oh, okay. So sklearn doesn't, okay, I've been working with Torch and Transformers too long. sklearn requires you to use pickle still. Or I guess they don't require it, but pickle's an easy way to save these models because they don't get very big, and so unpacking them is easy. And so basically all we want to do is with open, and you do, we can call this one sgd dot pt, we'll do pkl. These aren't PyTorch models, and we want it in write binary mode. Pickle dot dump, and we want to dump sgd into the file. And we can do the exact same thing with our multi-layer perceptron, except we're going to change this to MLP. Same with this, MLP. And you'll notice both of these binary files just got written. Okay, yeah. These are impossible to read for us, but they're binary files that contain the weights of the model as they were trained. And then you can load them again just by doing sgd equals, oh, I guess we have to do this again. But we're going to initialize it with read binary instead of write binary. And we're not saving anything, and we'll do sgd equals, or sgd2 equals pickle.load. And then you can do sgd print sgd2.predict and give it anything. We'll give it a 1-1 and see what it does there. Oh, it needs 2. Perfect. So this is how you save and load these models that you're creating, exactly like how we do in the GitHub in WildTrueLearn, those DLLs, so that you can actually save the models that you created with sklearn and then load them again later to predict new things if the data sets are similar. Or you can call fit again to train an already trained model on a new data set Really, really cool stuff. I hope that you enjoyed this video, and I will see you in the next one. The last one is recurrent neural networks. It's the last thing that we use in While True Learn, and I'm excited. This is a big momentous moment for this playlist. So I will see you in the next one.